So let's try to understand the whole thing about lexicographic ordering. The basic idea is very simple. Let's consider a grid where, for example, I set n to be equal to 3 and m to be equal to 4. That means along here I have x0, x1, x2, x3, x4, and along here I have y0, y1, y2, y3, y4, and y5. Then the equations that will govern the values of u that we're interested in will have something to do with the purple dots in here. So we will have 3 times 4, aka 12 equations. Normally what we do is we call the solutions in here something that has to do with the index that they correspond to in the grid. So we have u11, u12, u13, u21, u22, no, not u22. I'm very bad at counting. u31, u41, u42, u43, u33, u23, no, I got it wrong again. Let's try again. Sorry. Okay, so u11, u21, u31. Great. And then u21, no, not u21, u12, because it's I comma j. These are the j's and these are the i's. Oh my god, this is so hard. u13, u14, u24, u34, u33, u32, u31, which I already have, and then I have u2, u23. Okay, so that's the indexing we're used to here. Now the thing is, well, we have 12 equations. We want to put them into a matrix system. So the easiest way to do that is to change our indices such that they just run from 1 to 12, and then have the matrix system where the coefficient matrix is just 12 times 12, instead of having 4 3 times 3 matrices, which will probably just confuse us even more. So lexicographic ordering is a way to convert double indices into single indices. And the way we do that is we start by counting along the first coordinate. So we hold the first coordinate, and then we call this v1, v2, v3, v4, and then we go down here v5, v6, v7, v8, v9, v10, v11, v12. So the reason it's called lexicographic ordering is because, well, it's more or less how you order things in a lexicon. You start out by the first letter, and then you consider what comes first in the second letter, and then when you finish that for the first letter, you just go on for the when you finished varying through the second letter, then you go to the next value of the first letter, which is 2, and then you look at the second letter, and then you go to the next value of the first letter again, etc., etc. So lexicographic ordering makes a lot of sense. Probably sounds more confusing when I try to explain it. So the thing is, it's important for us to know how to convert the indices between the lexicographic index here and our normal index that we use. For example, v10, if we were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we will find that v10 corresponds to u3.2. And v12, for example, corresponds to u3.4, and v3 corresponds to u1.3. So the question is there some kind of general a conversion that we can make that will help us probably with our programming. So for example, if we consider some VL, then the first coordinate of the first index of U, which is the I index, will be given by the floor value of L divided by M. So let's try to test that. For V10, let's take 10 divided by 4. Well, that's not right. Sorry, not the floor value. This should be the ceiling value. The ceil value. So for V10, let's try that out. We have 10 divided by 4, which is equal to 2 point something, and that ceil is 3, so that's right. And then what we do is we want to take, well, this is also wrong. Everything I've written in this formula is just plain wrong. So let's try to make this formula together instead. So I want to find the I index of U. That was, as we established earlier, just equal to L divided by M, and then we round that up to the nearest integer. And the reason that works is because, well, let's consider the I index can be 3 different values, and for each time L goes above some multiple of 4, the I value increases by 1. So that's why it's important that we divide by 4 here. And the rest is just kind of like common sense. You look at an example, for example V10, and then you consider 10 divided by 4. That's 2 point something, you round that up, that's 3. The greatest value of L, for L going from 1 to 12, is 12. L divided by 4, that's 3, so you end up here. For example, if you try it with 8, then you have 8 divided by 4, that's 2, so you've got the right I value as well. If you try it with 3, with 9 divided by 4, that's 2 point something, round that up, you get 3. Okay, and so what should we have over here then? Well, what we should have over here is essentially what is left over after you've counted all the values of all the values of L that come before the start of the column that you're in, if that makes sense. So I'll just write up what I mean by that. What I mean by that is the J value should be L minus the I value over here multiplied by M. So let's just take an example. For L equal to 10, this number is equal to 3. And I'm not saying M, am I? No, not M. I think it should be M minus 1. M minus 1 multiplied by so this, or no, it should be this minus 1 multiplied by M. Great, that's how we do it. Okay. So let's try with 10. We have L equal to 10, and then I want to remove 3 minus 1, which is 2, 8. So 2 times 4 equals 8. So 10 minus 8 equals 2. Yay! Okay, so let's try it with 12. You have 12 minus, well, this is 12 divided by 4 minus 1. That's, let me see. 12 divided by 4, that's 3 minus 1, that's 2. 2 times 4 equals 8, and 12 minus 8 equals 4. Yay! and then you can test this out. I'm quite sure that this formula works. So this is how you go from an L value to finding the value of I and the value of J. And if you want to find out how you find an L value based on I and J, then you just look at formula 618. Okay, so to go the other way around, just look in the book for formula 618. Well, now I think we've beat this horse enough times, so let's just move on to the next part, which has something to do with positive definiteness of the matrix A, which you will construct according to the book's section 621. So if you just construct A as they do in the book, it's more or less precisely the same A, because you can consider why your problem's left-hand side actually doesn't change, so neither does A. The thing is then that afterwards you have to argue for whether A is positive definite or not. I can tell you, yes, it is positive definite. In the next video, we'll talk about why it is so.